Hi everybody, this is Mostapha Kalami from Yarpus, and in this video tutorial we're going to learn about principal component analysis, or simply PCA. PCA is a method for dimensionality reduction and for feature extraction, and it's an unsupervised learning algorithm, and it is in some sense the mostly used unsupervised learning algorithm in the field of machine learning and artificial intelligence. Actually, PCA is a linear transformation which transforms the given data from n-dimensional space to another space with the same number of dimensions. But despite the fact that the original space, the original data has some correlations among the space variables or dimensions or features, always the resulting data in the target space will have variables which are completely uncorrelated to each other, and they are mutually orthogonal, or they are mutually perpendicular to each other. And let's see how PCA does this work and how it can be used to reduce the number of dimensions and reduce the dimensionality of the given data. Okay, let's see a simple description of the idea behind PCA. Assume that you have some data points in a two-dimensional space with two feature variables, x and y. For example, if you're studying some patients, then x can be the blood pressure and y can be the heart rate. And if you're studying some stock market assets, then x can be the return and y can be the risk. Simply, you have these two variables representing our data points in two-dimensional space. We have these samples. This is our sample set. And if you're asked to select just one of these variables, x or y, then which one of them are you going to select, x or y? It's a wise choice to select the variable with higher variance. And here it seems that x has higher variance because the variance of a variable is somehow proportional to its range of variation. And if you, for example, plot these lines of boundaries of variable x, then the variance of x will somehow proportional to this amount. We call it alpha. And if you show the variance range of y, that will be this, and the variance of y will be somehow proportional to this amount. And it seems that selecting x will result in a higher variance, and it will be a wiser choice. But if we are not limited to selecting just a single feature variable, and instead of that, we're allowed to form a new variable named z, which is a linear combination of x and y. c1 times x plus c2 times y. This is a linear combination of x and y. And z is a new variable, and if we're free to choose any value for c1 and c2, but with some restrictions in their sizes, for which value of c1 and c2 we will have the highest possible variance for variable z. And you know that selecting x or y is a special case of this general combination. And for example, if you select c1 equal to 1 and c2 equal to 0, then z will be simply equal to x. And if you select c1 equal to 0 and c2 equal to 1, then z will be equal to y. And the question is this: which values of c1 and c2 will result in the highest possible variance for variable z? And we must convert this problem to an optimization problem, and we will solve this problem using some optimization techniques. Okay, let's convert the problem into an optimization problem and solve to find the best coefficients to form such linear combination. Let's add a new page. We had this linear combination C1x plus C2y. Let's rename x into x1 and y to x2 and C1 to u1 plus u2 and define z as this. And let's add some other feature variables here up to n, for example, un, xn. And it's a generalization of this two-dimensional form. Let's define x as a vector which contains x1, x2 up to xn. And let's define u as a vector too that contains u1, u2 up to un. Then we can express z as an inner product between x and u, or u dot x, or u transpose x, or simply x transpose u. All of them are equal, and all of them equal to this linear combination of elements of x1 with coefficients u1, u2, and un. And the problem is to find the value for u1, u2, and un to maximize the variance of z. And the way we have x's here. Let's assume that we have this sample set x, which contains first sample x1, this is a vector, and x2 up to, for example, n samples. And we know that any of these samples are vectors given in some space, for example, with this component, the first component, the second component, and we can use D as our final component, and the D is, we can rename this N to D. This is the dimensionality of our original data. And all of these samples are vectors in this space. We can refer to as R to the D. We have these samples, and also we have this sample mean, which can be calculated by summing up all of these vectors from I equal to 1 to n, and we divide this summation by the definition of the mean value or average value. And if we want to calculate the variance of x or covariance of x, we can define this with covariance of x, which equals to 1 to the n, summation of, for I from 1 to n, and xi times xi transpose. We're going to ignore these vector signs here, and this is the definition of covariance of our samples, and I'm going to denote this with C, matrix C, which of course is a matrix of the size D by D. It's a square matrix, and generally it is positive semi-definite, and all of its eigenvalues must be positive or non-negative, generally speaking. And let's calculate the variance of Z2. The variance of Z can be defined in this form. It's the summation of Z minus Z bar. That's the average value of Z's, and you know that Z's are all scalar values. And we sum the squared value of this difference between any sample of Zi with their mean value, average value, and we sum up these squared errors and we divide them by the number of samples. And we know that Zi is U transpose Xi. For any of Xi's here in our sample set, we have a corresponding value in the Z space or Zi, and that's the scalar value. And U is the linear transformation which transforms our d-dimensional space into a single-dimensional scalar space. And if we want to calculate the Z bar, we know that is given by 1 to the n summation for I equal to 1 up to n and Zi. And if we put this into this, we can calculate and simplify it, and we can bring U transpose outside of the summation because it's independent of I, and you can factor this way, 1 to the n, I equal to 1 up to n, xi. And we know that this is the sample mean. It's the average value of all xi vectors. This is a vector 2, and you see that this is U transpose X bar. And if we substitute this relation and this relation into the definition of variance of Z, we get variance of Z will be equal to 1 to the n, I equal to 1 up to n, and U transpose Xi minus U transpose X bar squared. Okay, let's copy this. We go to the next page. Okay, we have this relation here. We know that A transpose B generally equals to B transpose A, and we can switch these multiplying vectors. Let's defactor this squared value as this, 1 to the n, or I from 1 to n, U transpose Xi minus U transpose X bar times U transpose Xi minus U transpose X bar. And now we can switch the vectors of the second term, U transpose Xi minus U transpose X bar, and Xi transpose U minus X bar transpose U, and they're equal. And now we can factor U transpose from left hand side and U from right hand side, and we can get this U transpose Xi minus X bar and Xi transpose minus X bar transpose U. And we can have the transpose sign outside of this parentheses, so I'm going to rewrite this term Xi minus X bar transpose, and now we can factor and have the U transpose and U outside of the summation. Let's have this. We have the variance of Z as U inside bracket 1 to the n summation from 1 to n, Xi minus X bar, Xi minus X bar transpose, and U. We have U transpose here and U here. And we know that this is the covariance of our sample set, and we denoted this with C. So the variance of Z will be equal to U transpose CU, given that C is the covariance matrix of our sample set. So that's it. We reduced the definition of variance of Z to this form. We simplified that, and we want to maximize this amount. And you see that we can simply put U equal to infinity or 10 to infinity to maximize this amount. So we must have some limitations on the size of this vector, and we'll limit the size of vector denoted by norm of U equal to 1, or U transpose U, which is the squared norm of U, equal to 1. And to make the competition among u's fair, you cannot go to infinity. We search among all of unity vectors with length of 1 to maximize this variance. And that's a fair competition. So let's finalize the definition of our optimization problem. We want to maximize this amount u transpose cu. This is the variance of z, and we are limited to this u transpose u equal to 1. The size of vector, the transforming vector, must be exactly equal to 1 to have a fair competition. Okay, and what's the solution of this problem? We have constraint here and we have an objective function. Let's form an auxiliary objective function in this form, u transpose cu, and we use Lagrange multipliers to augment the constraint into our new objective function, minus lambda times u transpose u minus 1. And this is the Lagrange multiplier. And we know the solution of this problem can be found by setting the derivative of this j, this cost function, this objective function, with respect to u equal to 0. And if you calculate this derivative, you'll get the derivative of u transpose cu. This is a quadratic term, and its derivative will be a linear term in this form, cu, and the derivative of this term will be minus lambda u, and if we set this equal to 0, we'll get this equation, cu equals to lambda u. And you see that this is a familiar equation. If you're familiar with eigenvalues and eigenvectors in linear algebra, you know that this is the definition, the very definition equation of the eigenvalue and eigenvector. If C is a square matrix, then U is an eigenvector of that matrix, and lambda is the corresponding eigenvalue. So this is the eigenvector, and lambda is the eigenvalue. And that's it. The answer for our question is an eigenvector of the covariance matrix of our sample set. But which one of eigenvectors is the solution? Let's simplify the objective value here using this relation. We want to maximize the variance of z, which equals to u transpose cu. And we have cu equal to lambda u. And let's substitute cu with lambda u. Exchange that. We have the variance of z equal to u transpose cu, which equals to u transpose lambda u. And we know that lambda is a scalar value, and we can switch between u transpose and lambda u transpose u. And from this condition, this constraint, we know that this must be equal to 1. So the variance of z will be equal to the eigenvalue. And here, if we want to maximize the amount of variance, then we must choose the eigenvector corresponding to the largest eigenvalue of this matrix. So if we set lambda equal to lambda max, and we select u as the corresponding eigenvector of this eigenvalue, then we found the linear combination, the transforming vector u, which maximizes the variance of z. And that's the solution. If we are asked to select just one variable or form a single variable in this form, z equal to u transpose x, then the answer is the eigenvector corresponding to the largest eigenvalue of the covariance matrix of our sample set. If we consider this equation as a transformation, we have this equation z equal to u transpose x, and this equation maps the r-dimensional space of our sample set, which x belongs to this space, into the scalar or one-dimensional space of R. And this is done by this linear transformation. However, if we want to map this d-dimensional space to m-dimensional space, then what? What we can do to select or form such a mapping in the general form of z equal to u transpose x. And u here is a matrix, and if we assume that x is a member of Rd, or that's a matrix of size d by 1, and z is a matrix of size m by 1, it's a vector, then u transpose must be of size m by d, and u itself must be of size d by m. And if we show this u by its columns, then we have some vectors u1, u2, up to um. And all of these vectors, these are all vectors, columns of this matrix, which is of size m d by m. uj is a vector in this space, in our original space, just like the single vector case. This time we have m vectors. And if we solve this problem and want to maximize the variances of these components, the resulting components of z, which are known as principal components, then we end up with selecting eigenvectors of the covariance matrix C as our columns. These are all eigenvectors of this covariance matrix, and they are sorted in descending order of eigenvalues of this matrix. So, for example, if we have this covariance matrix and it has these eigenvalues, lambda 1 greater than or equal to lambda 2, and generally we ignore this equal sign, and to lambda d, and their corresponding eigenvectors are u1, u2, u3, and ud. And if we want to preserve the most possible data by selecting some of these transforming vectors, then we must choose them according to the descending order of our eigenvalues. These are eigenvalues, and these are eigenvectors. And for example, if we want to map some data, some sample set to R2, then we must compute the covariance matrix of this sample set, and we set this as C, denoted by C. Then we compute its eigenvectors. This lambda 1 is the largest eigenvalue, and its corresponding eigenvector is u1 and u2, lambda 2 and u2. And then we use this transformation u as u1 and u2 to transform x into R2 by this equation. Z, this is a vector, goes to u transpose x, and this is a vector 2. But this is from R2 and this is from RD. And by choosing use our transforming vectors or columns of this transformation matrix as eigenvectors, and according to descending order of eigenvalues, then we ensure that two components of Z have the largest possible variances among other possible combinations. So that's it. This is the idea behind principal component analysis. After this, we will implement PCA step by step in both Python and MATLAB, and then we will use the available toolboxes and libraries to perform principal component analysis efficiently on any given dataset. Okay, let's start with a Jupyter notebook, a Python notebook, and perform calculations needed for principal component analysis step by step. And I'm going to use NumPy here, and I'm not going to use any predefined functions or available library to perform principal component analysis, just matrix calculations and operations. Okay, let's import NumPy as MP, and let's import matplotlib.pyplot as PLT, and let's set the flag for matplotlib inline to have the plots inline just in this notebook. And let's run the cell. We imported everything needed to perform calculations and have the results as plots. I'm going to create some random data, and to make the results reproducible and repeatable for you, I'm going to create a random number generator, RNG, equal to mp.random state. And if you want to make a random number generator with a predefined seed, you can pass an integer from 0 to the power of 32 minus 1. Any number in this range is available. I'm going to set this to 0. And that's it. I created a random number generator. I'm going to create some samples of normally distributed numbers, actually 2 components, and a couple of observations of that 2 random numbers. I am going to use rng.randn. This creates standard Gaussian numbers or normally distributed numbers with mean value of 0 and variance of 1 or unity. Okay, 1,000 observations of 2 components. I create this matrix here, and that's a matrix with 1,000 rows and 2 columns. And let's plot this matrix using scatter command of matplotlib, and I'm going to plot the first column versus the second column, and let's run this command. You get this plot, and you see that the unit length, the length of unit for this axis, for x-axis, is not equal to the y-axis, so I'm going to use the axis command here to set the axis mode to equal, to make the unit equal for both directions. And I'm going to set the grid on for this plot, and let's run this, and we have this. We have 1,000 samples of 2 components on the plot, and you see the overall shape is circular, and if you watch from any angle to this shape, you'll get similar values for variances. But I'm going to change the shape of data by some matrix multiplication, some matrix operations using a random matrix. For example, A equals to RNG dot rand. It's a uniformly distributed random matrix, and 2 by 2. That's it, because we are going to change 2-dimensional data. Let's run this, and we have this matrix, and we have 1000 by 2 matrix here and 2 by 2 matrix here. I'm going to create X as mp dot w by A. I'm going to multiply W by A, and if you multiply these matrices in this order, you will get a matrix of size 1000 by 2, same size as W. So let's run this, and if you plot X using the same functions, same commands, you'll get this plot, and you see that the shape is changed now. And if you calculate the variance of first column of X, you'll get this value, and if you calculate the variance for the second column, you'll get this value. So selecting the second variable here, if we want to select just one variable, leads us to have larger variance. However, it's not the optimum solution. By eye, watching in this direction leads us to have much more variance than selecting, for example, the second component. And we're going to find this direction using the principal component analysis. Okay, I'm going to calculate the covariance matrix using the command mp.cov, and I'm going to pass x, but here we must pass x transpose to this function to have the covariance matrix. I'm going to print C itself, and this is the covariance matrix we have. And if we want to find the first principal component, we must use the eigenvalues and eigenvectors of this matrix. And to calculate the eigenvalues and eigenvectors of this matrix, we must use the functions defined inside the MP or NumPy. Okay, I'm going to call mp.linalg.eig for C. And if you call this, you'll get a tuple, and it has two members. The first one is the eigenvalues. You can refer to it as E, and the second one is a matrix which contains the eigenvectors. Let's run this. We have E here. These are the eigenvectors of our covariance matrix, and we have V, and this is a matrix, and columns of this matrix, this and this, are eigenvectors of this matrix, the covariance matrix. So this is the first eigenvector, and this is the second eigenvector, and this is related to this eigenvector, and the second one is related to this eigenvector. And if we are going to select the eigenvector corresponding to the largest eigenvalue, then we must choose this. Okay, let's define U as V and its second column. That's it. We have U as the eigenvector corresponding to our largest eigenvalue. And this is the, if you see the shape of this, you'll see that this is a vector with two members, and this is a one-dimensional vector and a one-dimensional matrix actually. And I'm going to calculate Z. Z will be equal to MP dot, and that will be X and U. I'm going to calculate this, and here, if you get the shape of this, you'll get 1,000 scalar values as a vector. And if you calculate the variance of this Z, mp.var z, then you get this value, 0.52. That's equal to this eigenvalue, exactly. It must be equal to this. And this is larger than these variances for first variable and the second variable, for first column and second column. It's larger than both of them. And that's it. That's because PCA works. It finds a direction of watching into data to get the maximum possible variance. Okay, and let's see the equivalent of these data on the projected, on the first principal component, and see if we are going to code X into Z. If we decode this into some variable, for example, X hat, what we get? These are the projections of data we have. And actually, if we calculate this, we'll get something like this. We have these data points, and we get this direction for our principal component, and they are projected onto this line by the transformation, and we have these data points now. And this axis is Z, And instead of dealing with two-dimensional space, x and y, we just work with one dimension, and our data points are projected onto this direction, this axis. And let's find these equivalent or encoded data points and plot them on x as well. To find them, we must find the decoded variables here. These are the decoded. To find the equivalent of these z's on two-dimensional space, we must decode them. To do this, we know that we must use the U transpose, because U transpose is in some sense the inverse of U. Why? Because MP.U by itself, its inner product by itself, is 1. And we have some numerical errors here, but in theory it must be equal to 1. And now we're going to find the multiplication between Z and U transpose. And to do that, we use MP outer, the outer product between Z and U transpose. And that will work. If you want, you can simply use U instead of U transpose. It will work fine. And I'm going to name this as Y, for example. And oh, sorry, I have a misspelled function here. And if you get the shape of Y, you'll get 1000 observations of two variables, but its two components are completely correlated to each other, and they are on this line. And this line I plotted here. And I'm going to plot these. Let's copy this code. And after this, I'm going to plot Y as well as this. And let's have the results. Here we have the results. And these are the projected versions of original data along the first principal component. And if you repeat these calculations using another vector, for example, V, the first eigenvector, then you will get a direction perpendicular to this direction. And this is the way PCA works. And in this way, we can project and transform our two-dimensional data into another two-dimensional data space. And there, in target space, we have completely uncorrelated and mutually perpendicular data components. And if we want, we can suppress as much as data from the smallest eigenvalues, and using this technique, we can reduce the number of dimensionality for any given dataset in an unsupervised manner. And remember that PCA is an unsupervised learning algorithm. And because we didn't use any labels or target values to perform principal component analysis. And that's it. It's an unsupervised learning algorithm. And in some sense, I said before, in some sense, it is the mostly used unsupervised learning algorithm today. Okay, we performed principal component analysis step by step, and we reviewed the theory of PCA in this notebook. However, next we're going to use scikit-learn to perform principal component analysis on a larger data set, and we'll see what capabilities scikit-learn has in its principal component analysis function and class. In this part, I'm going to use scikit-learn to perform principal component analysis. First of all, I imported NumPy and Matplotlib, similar to our previous notebook, and I'm going to import from scikit-learn the datasets submodule, and I'm going to import from scikit-learn another class in the decomposition submodule, which is PCA, capital PCA, remember that? And that's it. We imported datasets, which includes some well-known and famous datasets available, and we imported PCA to perform principal component analysis. Okay, let's import the Iris dataset. Iris is a well-known dataset which contains some samples of flowers, actually 3 types of flowers, and the features measured and gathered in this database are 4 variables actually: the widths and lengths of petal and sepal parts of the flowers. Okay, let's import using the datasets.load iris, and that's it. We have the Iris datasets here. The inputs of Iris dataset are available from iris.data, and also the target values are available from iris.target. And if we check for the shape of X, we get 150 samples of 4 variables, and for target values we have 150 scalar values for labels. Okay, let's reduce the number of the dimensionality of our input space from 4 to 2 principal components. To do this, we must create an instance of PCA class. PCA equals to PCA with 2 components, and you can call this using this notation or use the named arguments n underscore components equal to 2. And now to create the principal components of data, to find the principal components of data, you must call the fit function of this object PCA on this data X, and you will get a PCA object as output of this process. But you can check for PCA.components, and these are 2 components of PCA, principal components, and you know that these are the eigenvectors of covariance matrix of this set of observations. And you see that they have, both of them, they have 4 components. Okay, let's transform this X into our feature space, our principal component space. To do this, we store the transformed variables in a variable named z equals to PCA dot transform X, and that's it. If you check for the shape of this, you'll get 150 samples of 2 variables. So PCA reduced the number of dimensions from 4 to 2. This transformation has preserved most of data in it, and we can plot components of z to see how much amount of data is preserved during principal component analysis. Okay, let's plt.scatter, use the scatter function to have a scatter plot of z, and we use the first column, we plot the first column versus the second column, and if we plot this, we get this plot, and we can use y as our color info to plot the classes with different colors. So we have this plot as the result, and we have 3 classes here, and you see that one of classes, even in 2-dimensional space, is completely separable from the other 2 classes, and the 2 classes are also separable with some level of accuracy in this 2-dimensional space. And that's it. We preserved the data behind this 4-dimensional data space, and we use just 2 principal component, and we see that we can still perform classification on this. So PCA is a kind of preprocessing which reduces the number of dimensions and number of variables and makes the task of classification, regression, or other computations and analysis on data much more easier. And handling 2 variables, of course, is easier than 4 variables. Okay, that's it. That's how scikit-learn uses principal component analysis. As another example, I'm going to work with a dataset of handwritten digits. And that database is available in scikit-learn too. So I'm going to load that dataset into a variable named digits. Digits equal to datasets.load digits. And if we check for data inside this, oh sorry, I dropped an A here, we see that 1797 samples of 64 variables are available in this dataset. So we have 64 dimensional space, and we want to reduce the number of variables to 2, for example. Let's check for it. And what are these 64 variables? If we check for digits.images.shape, we have another field, another member for this class, images, which contains the same number of samples of 8 by 8 matrices. Actually, our inputs are images of 64 pixels, and they reshaped the input data and presented as square matrices here. And if you want, you can see what does it look like, and you can use plt.imshow or matshow to plot one of images, digits.images, for example, the first one, that's the 0. And you can also set the color map to gray to have a grayscale image here. And if you, for example, plot others, this is 1, and this is 2 as well. And for example, you can provide 5 to 8, and I think that will be 8 because of this digit here. And you have images of these two, but they reshaped these images and created a row of 64 numbers. And also we have digits.target.shape 1797 target values, scalar target values, which contain the equivalent, the numerical equivalent of this image. And this database, this dataset can be used to train supervised neural networks or other algorithms to detect the number from images. Okay, but let's see if it is possible to reduce the number of variables from 64 to just 2 variables, 2 principal components. Yes, that's possible, and we are going to use principal component analysis to do this. Let's create another instance of PCA here, and let's set the number of components to 2, and let's fit this model to digits.data, and that's it. And let's transform our inputs two-dimensional space, and that's it. If you check for shape of this, you have the same number of samples which include just 2 variables. And let's plot this z. So plt.scatter z, the first column here, and the second column here. And let's use the target's information as color. C equals to data.target, digits.target, sorry. We have this, and let's change the color map, for example, to tab 10. And that's it. And let's add some level of transparency to this plot. I use 0.7, 70% of transparency. And let's add some color bar to this. To do this, I'm going to plt.color bar, and also we can use plt.grid on as well. And we have this plot here. We have 10 colors here for digits 0 to 9. And here you see that this color represents 0. And 0 is almost separable from other digits, even in this two-dimensional space. But they have some similarities to this color, and that's 6. And they're visually similar. Makes sense. And 1 here, 1 is not so similar to 0, so they are not close, even in this two-dimensional space. 2 is here, 3 is here, and 4 is here, and we have 5 here, and it is somehow similar to 9, 3, 2, and other digits, and 8 as well. And we have 6 here, and 7 here. 7 is very similar to 1 visually, and they are close to each other in this space. And we have 8 here, and we have 9 here. And 9 is very similar to 5, and they are close to each other. So you see that principal component analysis preserved a notable amount of data. And if we, for example, use principal component analysis with 4 or 5 components, then the preservation amount will increase, definitely will be increased, and we can classify the images and we can perform classification on these images with much more amount of accuracy. And you see that it works. It is very good at reducing the number of dimensions and performing pre-processing on data, and reducing, for example, from 64 numbers of dimensions to 5 or 4 dimensions helps very much the algorithms to work better and more efficient on data. So that's it. We performed PCA using scikit-learn, and you can refer to documentation of scikit-learn to see other examples of principal component analysis. Next, we are going to use MATLAB to perform principal component analysis, and we'll repeat the same for MATLAB from scratch. After implementing PCA in Python, I'm going to do same in MATLAB, and we'll start with creating some random data points, two-dimensional space, and then find the principal components of the data generated by random generator. Okay, let's start with a matrix W, which is random number with normal distribution. And we have, for example, 1,000 samples of 2 elements. And let's create this. See, we have 1,000 by 2 matrix here. And if you scatter plot this W, its first column, by its second column, then you will have this plot. And you see that the general shape of this plot is circular, and watching from any direction to this data will result in similar value for variance. For example, if you calculate the variance of W in first column, you'll get this, almost equal to 1. And if you calculate the variance for the other direction, for second variable, you'll get this. And in theory, they must be equal to 1, but because we have just 1,000 samples here, then we have some errors. However, if you increase this number, 1,000 sample, to 10,000 or 100,000, you'll get numbers closer and closer to 1. And watching from different directions to this data will not make difference. We need a data to have some differences, and in real-world applications we have such data in all cases, and so I'm going to remap this data to make it similar to data available in practical problems. Okay, I'm creating a random matrix, 2 by 2 matrix here, and I'm going to multiply this by this to get a matrix X, which equals to W times by A, matrix multiplication, and we get this And to suppress the output, we put a semicolon to this. And I cleared the screen. We have x here. X is given by this. X and W have same number of elements, and A is a 2 by 2 matrix. Okay, if I scatter plot X just like W, then this is the shape of data. And in real world applications, we have data similar to this. And I'm going to perform principal component analysis on this data. Okay, to do this, I'm going to calculate the covariance matrix of X. So the cov of X will be this. And if I ignore this, I get the covariance matrix of this X, and the eigenvalues and eigenvectors of this covariance matrix will help us to find the principal components. Okay, using the eig function, I'm going to find the eigenvalues of this. However, if you call the eig function using two outputs, for example, A and B, then you get a matrix which contains eigenvectors of C as columns and a diagonal matrix which contains eigenvalues as its diagonal elements. And we rename A as V and B as E for eigenvalue. Okay, so let's rename these values. V is the eigenvectors and E contains eigenvalues of this matrix C. So we have the largest eigenvalue here as the second, and its corresponding eigenvector is the second column of V. So U, or our transforming vector, is V and its second column. Okay, now I'm going to find the value of Z, the first principal component. The relation and the equation behind the transformation was U transpose X. However, here U is a 2 by 1 matrix, and X is a 100 by 2 matrix. So if I'm going to calculate this dot product, then simply X times U. X is a 1000 by 2 and U is 2 by 1, so we can multiply them and we get 1000 by 1 matrix. So we have Z as this, and let's see what's the variance of Z. You see that is almost 1.7, and if you calculate the variance of X in first column, you'll get this, and if you calculate the variance of X in second column, you'll get this, and the variance of Z is larger than both of them. So we found a new direction, a new variable, which is a linear combination of both X variables, and we have the largest variance possible. Okay, now let's decode this variable to have the projected values here. To do this, we have Z here and we have U here, and we can multiply this Z by this U to have some decoded variables. Okay, we multiply Z 1000 by 1 by U transpose, and this is 2 by 1 in its original form, and if I transpose this, I get 1 by 2. And 1000 by 1 and 1 by 2, I get 1000 by 2 matrix. So that's it. We have this, and it has same size as X, and I'm going to plot these together, X and Y. Okay, let's create a new figure, and let's scatter X, the first column, X, the second column, and let's hold on to make possible to plot another scatter plot on the first one. I'm going to plot the first column of Y versus the second column of Y, and this is the result we have here. This is X, and this orange line is the Y, the projected values of our original data. And you see that if we watch in this direction, perpendicular to this line, we get the largest possible variance from data. Okay, I'm going to gather all these inside a script and have a fully functional PCA program. Let's open the editor here, and I'm going to clear the screen, clear the workspace, and close all other figures probably open. I'm going to create a W rand n 1000 observations of 2 variable, and I'm going to create a 2 by 2 matrix here, and I'm going to calculate X as W times A, and this is our data, generate data. And let's calculate the covariance matrix. We have C equal to co of X, and finally we have find PC1, first principal component. We find the eigenvectors and eigenvalues of this matrix, and I am going to save this as PCA1. And if you want to do the comparison automatically, for example, here we calculated the eigenvalues and eigenvectors, then, for example, we found this without any calculations. However, we can get diagonal elements of this matrix, and we can find the maximum value. We have the max function in MATLAB, and if you see its documentation, max returns the maximum value, and if we get 2 output variables, it will return the maximum index here. Okay, so we can find the eigenvalues of this matrix by finding the diagonal elements of this matrix, and Emax as the maximum eigenvalue, and Emax the index of, or Emax end simply, will give us the maximum value of eigenvalues and its index. You can simply put, instead of diag E, and remove this line, and if you don't want to, you can ignore this as well. And I'm going to have this value to do a comparison later. Okay, U is V, and which column of V? The column which is indicated by Emax end, which is the eigenvector corresponding to the maximum eigenvalue of the matrix. Okay, let's run this. I'm hitting F function key 5, and we have E here, and we see that the second eigenvalue again is the largest value, and we have Emax, and we have V here, and U as its second column. Okay, let's transform data and have Z equal to X times U, and let's decode or untransform data, and we have an approximate version of this, Z times U transpose, and we calculate these, and we have Z, Y, and X, and we're going to, for example, calculate the variance of Z here, and we have Emax. Okay, they must be the same number. We reviewed the theory. Our objective function was the maximizing the variance of Z, and later we found that the value of variance for Z equals to the eigenvalue of the matrix, a covariance matrix, and it's true. And finally, we plot results. Let's create a figure here and scatter X first column, X second column, and hold on, scatter Y first column and Y second column, and let's run the program, and we get this. We have the data, and we have the first principal component here. And that's it. We wrote PCA for a single dimension, and we found the first principal component of a random data from scratch. Okay. Let's do another example on Iris dataset we've done for Python. I'm going to load Iris dataset here, and I'm going to perform PCA on that. Okay, let's load the Iris dataset. I'm going to call the documentation of Iris dataset. You see that calling this function will return two variables, one for inputs and one for targets. So I'm going to define two variables, x and y, and I'm going to call the Iris dataset. X is 4 by 150 matrix and y is 3 by 150 target values. And actually we must transpose both of these matrices to make them appropriate for calling PCA function available in MATLAB. So I'm going to transpose both of them. X equals to X transpose and Y equals to Y transpose as well. And now we have 150 observations of 4 components, and Y is the 150 target values of 3 binary values. So we have this here, and we can, for example, convert this from this vector notation to some index notation. So it can be done by this as vec2 end this Y transpose here, and you see that it converted this to 1, 1, 2, and 3, and you can set this Y equal to this, and we get this value. Okay, we have X, and beside that we have Y, so you see that we have these values for input and this for as output, and these values for input and this as output. And Iris dataset contains these 4 measurements of 3 types of flowers, and these 4 are widths and lengths of sepal and petal part of flowers, and 3 classes, 3 types of flowers are measured, and 50 of all of these classes finally gives us 150 samples from Iris dataset. Okay, I'm going to perform PCA on this, but this time I'm going to use the PCA function. PCA function accepts observations as rows of matrix. So this is the number of rows in our observations matrix. Our input matrix must be equal to the number of observations, and the number of columns must be equal to number of feature values, or dimensionality of our input space. I'm going to call this, and this will return the transforming matrix. And if I set the non-components parameter here to, for example, 2, it will give us the 2 principal components. And if I set this to, for example, 3, it will give us 3 principal components. Okay, let's continue with 2 principal components, and this is the matrix which transforms our data. However, PCA can return, beside this U, the transforming matrix, Z as well, and this is the known as a score, and we get Z as 150 transformed components in 2-dimensional space, and U is the transforming matrix. And if we multiply U by X, we'll get Z. Okay, now let's plot Z as a scatter plot, scatter Z, and its first column, its second column, and we'll get this. However, we can set, for example, 20 for the marker size here, and we can set color numbers according to Y, and we can set field flag here to get this plot, and it uses some color maps to plot this, and we can set simply color map to jet, for example, to have this, and or jet3. I think it might be better. No, jet is fine. Oh, sorry. I must call this and then this. Okay, and we have the plot of our principal components, the two most important principal components of Iris data set. Let's gather these parts into a script and have the final script. Here I'm going to create a new script file, clc clear close all, and I'm going to load the Iris dataset, and that's good. I'm going to transpose X. I'm going to vec to end Y and then transpose that matrix, and let's save this as PCA2. Let's run this, and we have this here, and let's have the transforming matrix and Z's as the output of PCA of X, and number of components to 2, and we can set this by a variable, for example m. And let's create a figure here. Let's scatter plot Z, its first column versus its second column, and with marker size 25 and with colors equal to Y and with field flag, and let's use color map equal to jet. Okay, I'm going to plot this, and that's it. We have two principal components of Iris dataset, and here we see, as we have seen in Python examples, one of classes is completely separable even in this two-dimensional space, and two of classes are very close but still separable in some levels of accuracy here, and we see that PCA preserves a notable amount of data from Iris data set. Okay, let's do this for the digits dataset. Okay, I'm going to perform PCA on digits dataset, and I'm going to load digits data into a matrix. Let's clear workspace and comments. Let's have the data here, CSV read and digits.csv. And this gives us 1,797 samples of 65 elements, but we had 64 inputs. The last column of this matrix contains the target values, so we have X as data from all rows from first column to end -1, and that's the 1 to the end of the matrix, and that means the 64 columns of the matrix is considered as input. So we have X here, and we can set Y or target value as data all rows, and the final row here, final column here, and that's the target value. This time let's do all of this inside a script, and let's create a new script, and I'm going to do this. We have inputs here, we have targets here, and if you want you can use, for example, im show to show the first image inside MATLAB. Sorry, 8 by 8, and that's the 0 here. And if you want you can display the images, related images of inputs as well. And if you want you can plot the image of X as, you know, you have the first image here, and you can reshape that value as an 8 by 8 matrix, and the maximum value of this is 16, as I know, and we can divide this by 16 to get a normalized image here, and you can call imshow on this to get this image, and this is the 0, this is the handwritten zero index, zero image. You can, for example, do for others, and this is a transposed version. I think we can rotate this and see the result. Okay, let's clear it and let's continue the script. Let's save this as PCA3, and I'm going to perform PCA on input and have the transforming matrix and Z using PCA on X and number of components equal to 2. Let's run this and we have Z, same number of samples and 2 components. And now I'm going to figure and scatter plot Z first column and Z the second column and use the 2025 as the marker size, and I'm going to use Y as our color data and field as flag. Let's run this and we see this. Let's use the color map as jet and see what rises here, and we can show the color bar as well. We can call simply the color bar function here and run the program, and you see that the 0 is dark blue and it's here. 1, some brighter blue is here, and this is 2, and this is 3, and this is 4, and 5 here, and 6, and 7, 8, and 9. And you see, for example, 0 is similar to 6 and they are close to each other. 1 is similar to 7 and they are close to each other. And 3 and 2 are similar and they are close to each other. 8 is similar to 7 and 9 and 2, and they are located here. And using 2 principal components, it seems that it will be hard to classify the data correctly. However, if you change the number of principal components, for example, to 5, then you can use this Z to classify the images, preserving more data. And I think you should check this using supervised algorithm, for example, a neural network, feed-forward neural network, to classify the numbers and solve this problem using, for example, 5 features. And I think we can preserve a very important amount of data. And if you want, you can calculate the amount of data preserved. For example, if you calculate the covariance matrix of X, we have this. And if you calculate the eigenvalues of C and store them in E, we have these eigenvalues. However, I'm going to sort this in descending order. And this is the sorted list of eigenvalues of this matrix. And, for example, we can calculate the sum of E here. This is the sum of all eigenvalues of E. And we can calculate the cumulative sum of this as well. And that will be this. And we can normalize this by dividing this by sum of E. And you can plot this, for example, and see that by increasing the number of eigenvalues and using more principal components, you preserve more data. And for example, if you want to preserve 80% of data, then I think we should use 13 principal components. And that will preserve almost or approximately 80% of original data. And you see that, for example, using just 30 eigenvalues and principal components, we will have 95% of original data. And this is the way PCA works, and this is the way it reduces the amount of data needed to work on data. Okay, we're at the end of our video tutorial, and I hope that this video tutorial was helpful for you. And in case of any question, suggestion, comment, please let us know on website of Yarpes or YouTube or wherever you're watching this course. And I wish you the best. Thank you.